This video is going to overview the senses of the ear, and I'd just like to start with a review of the anatomy of the skull, just to orient oneself. So here we have the temporal bone of the cranium. And notice that there's a prominent opening here, the external auditory meatus. So the elastic cartilage, which makes up the external ear, or the pinna or auricle, this collects sound waves and then directs it into the external auditory meatus. So here we'll get a closer look. So the vibrations of sound waves are directed here. And then all of the other portions of the ear, which I will be discussing, occur within the temporal bone. Actually, there's two parts of the temporal bone, the squamous portion on the outside and the petrosal. This is the petrosal portion. So the middle and inner ears will be inside the temporal bone. And if you were to look, take a closer look at that internal base of the skull, just like there was an external auditory meatus leading into the ear region, then the eighth cranial nerve carrying information about what we've heard will then pass through the internal auditory meatus to then reach the brain. And so then what we consider, the middle and inner ear, they exist there. Now, as I will review later, there's a hole in the middle of the temporal bone. So there's a cavity here. And this is where the inner and middle ear are located. And as we will see, there are actually little bones called the auditory ossicles, the malleus, or the hammer, the incus, the anvil, the stapes, the stirrup. There are these three little bones inside this cavity within the temporal bone. So just for reference, that's where the videos, discussing the ear are anatomically located. And so from the external ear, which helps to collect sound and direct it. This is important in amplifying sound. So for example, owls have such a distinctive face because their entire face is helping to collect sound waves and directed into the auditory canal. And this then represents the external ear. So the pinna and this auditory canal, this then represents the external ear, which ends at the eardrum. And this then is the middle ear. And then there is an inner ear, which we'll discuss presently. And so when there are vibrations in air molecules, because that's what sound is. So if you were, to be an A&P party where the music is very loud, and if you touch the wall, if the music is loud enough, you can actually feel the vibrations in the sound. Or if there's an amplifier and you put your fingers on it, you can feel vibrations. That's what sound waves are. And so the vibrations are directed here towards the tympanum, and that then causes the tympanum to vibrate. But now there's a problem. The problem is this tympanum, its freedom to vibrate depends on pressure, air pressure. And so, and forgive me, I'm kind of at a loss. I usually demonstrate this in a class. And in the class, I take door leading into the class and I rattle it to the, distraction of everyone in the hallway. So I rattle it and I say, all right, so that's, equivalent to your tympanum making sound. But now if I lean on it, it doesn't rattle as much. If the pressure on one side of the door exceeds the pressure on the other side of the door, it isn't as free to rattle. And the same thing here, if the vibration of the tympanum is going to then represent what we detect as sound, a change in pressure would be problematic, all right? Because that would then change how free this was to vibrate. It would then change how you hear. Well, does air pressure change? all the time. It changes from a sunny day to a rainy day. It changes if you're going in an elevator from the bottom floor to the top floor. It changes on an interstate from the bottom of the mountain to the top of the mountain. It changes when you dive or go scuba diving. And so here's a problem. This pressure keeps changing. But to hear best, we need the pressure on either side of this eardrum, this tympanum, then to be the same. Otherwise, you would, say, oh, I love listening to music on the top floor, not on the bottom floor. Or could we continue this conversation when the sun comes out? Because in rain, I don't hear as well. I mean, we don't want that. And so therefore, we need a way of balancing pressure on either side of this eardrum, because this pressure coming from the outside world is going to change. Well, in the classroom that I would teach in, I then just walk over to the window and I open the window. And I say, all right, so if a thunderstorm comes through, that will change the air pressure in the hallway. But if we open the window, this new air with the new pressure, it comes in the window in addition to coming in the hallway. So go back to the door. All right, even though there's new air in the hallway with a new pressure, then this new air is also coming through the window, and now the air pressure is balanced once again. And so that's the purpose then of this pharyngotympanic tube, all right, which ends here in the middle ear, but which starts in the nasopharynx. So behind the nasal cavity is an area of the pharynx called the nasopharynx. And this pharyngotympanic tube enters there. So if I go up in an elevator, there's new air with a new pressure here, but there's new air with the new pressure also going in my nose, also then through this opening to the pharyngotympanic tube, which reaches here. So that we have this pharyngotympanic tube that then allows air from the throat, the pharynx region, to then reach the middle ear. And thus we can balance air pressure on either side of the tympanum. And once again, that's how we hear best, when the air pressure is balanced. And we've all had this feeling that when you go up in an elevator or up in an airplane, you feel as if there's pressure in your ear and it's uncomfortable. But sometimes if you move your mouth or swallow, that will force the new air through the pharyngotympanic tube that then equilibrates. If you go scuba diving, well then, you have a pressure in your ear and you have to equilibrate. And so you have to stop until, this balances out. And sometimes you'll then just try to force, just by doing this, you'll try to force this new air up through that so that it equilibrates, and then you can dive deeper. The only downside to this is that if air can travel from the throat to the middle ear, then so can microbes. And there are a lot of microbes in the throat. And this then is the source of ear infections. Okay. Now, as we talk about the senses of the ear, it turns out there are multiple senses. And so when I was in school, the 8th cranial nerve was called the auditory nerve, because that's what we hear with. But then obviously we do more with our ears than just hear. So that's now why we call it the vestibulo-cochlear nerve, because in addition to hearing, there's also balance in the sense of acceleration. But even though the ear does manage these different senses, they are all detected through specialized epithelial cells known as hair cells. So a hair cell has a specialized cilium, and remember that all cells have a primary cilium, and that these can be specialized for sensory functions. So here we have this big kinocilium, which is a cilium. And then neighboring it are these modified microvilli called stereocilia. So here they are, and these structures give the cell the name of hair cell. And these can bend. And so these hair cells will either be in fluid, or they're in a fluid, but there's a gelatinous material around here, like the cupula in the semicircular canals, or the otolithic membrane in the vestibule. So either liquid or like a gelatinous material in the liquid that will move and then that will then move these hairs. And we detect that. So obviously, if the environment causes a change, we want to tell the brain, because ultimately we're telling to the brain, hey, I just heard something, or hey, I'm off balance, or whatever. And the way that we do that is that there are proteins which link the tips of the kinocilium and the stereocilia. And these proteins are linked to ion channels, which are mechanically gated. All right, and so when ion channels open or close, sometimes they do that with change of in response to a change in voltage or the presence of a neurotransmitter. Others are mechanically gated, so it is some mechanical change which causes them to open. And so when these hairs tilt, that causes tension on these ion gates, which then changes whether they're open or closed. And since there's this big kinocilium, we can actually measure movement towards or movement away from the kinocilium. So if these ion channels open, this then changes the amount of ions in the cell, which causes the cell to depolarize, become more positive, or hyperpolarize, become more negative. And at the base of the cell, these electrical changes then can lead to a change in the secretion of neurotransmitters. So it turns out that there are nerve cells of the vestibular cochlear nerve which are contacting this hair cell, synapsing with it. And in response to the distortion of the stereocilia and kinocilium, electrical changes lead to a change in the production of neurotransmitter, which then gets communicated to the brain. So as a result, the brain would now know these moved. Why would they move? Well, there are three areas of the ear that I would like to discuss. The first is the cochlea, and this is where the movement of hair cells will detect sound. All right, so when hair cells, distort here, then our brain perceives this as sound. In the semicircular canals, the hair cells there, when they are displaced, that gives us a sense of movement, like our head is moving this way or that way, which then also helps inform our sense of balance. And then when in the area connecting them in the vestibule, when the hair cells move, we get a sense of acceleration, that the car is accelerated or I'm going up in the elevator. So there are three senses perceived in the ear: sound, balance, and acceleration. And by acceleration, I mean both linear and vertical. And all of these are perceived by these hair cells. Okay, so going to the middle ear begins at the tympanum, and the vibrations in the waves which go through the auditory canal then reach the tympanum and cause vibrations there. Now, can we perceive these vibrations? Well, different animals perceive sound differently. Not all animals perceive sound well. So, for example, a rattlesnake can't hear its own rattle, I've heard. Mammals are pretty good at perceiving sound. And one of the reasons is for those auditory ossicles. There are three little bones, all right? So here's the tympanum, and touching the tympanum is the malleus, the hammer. Then touching that is the incus, and then touching that is the stapes, which then contacts the inner ear. So let me just go to a picture of those again. So here is where the middle ear is located, within the temporal bone. And here we have three tiny little bones: the malleus, which then contacts the incus, which then contacts the stapes. And then what happens is vibrations get passed one to the next. So the vibrations in the tympanum cause vibrations in the malleus, which cause vibrations in the incus, which cause vibrations in the stapes. And over the course of these events, the sound waves are amplified more than 20 times. All right, and so we will be able to perceive sound so much better because these auditory ossicles have amplified the vibrations. Reptiles only have one auditory ossicle as opposed to the mammals, which have those three. And so the vibrations are now, the stapes will then push on a region of the inner ear known as the oval window, which will displace fluid in the inner ear, which can then result in the movement of those hair cells, as we will see. Now, here in the vestibule, there's a little place that the stapes contacts, and it can push in, but then obviously if you're pushing a fluid, it might bulge elsewhere, and so then there's a round window next to it, so that when we push in fluid here, that will displace it, and then it will bulge outward on the round window. This region here is where sound is perceived. It's known as the cochlea. It looks like a snail because there is a straight tube which then has been coiled almost 3 times, so more than 2 times, almost 3 times, to form this coiled structure, which I will uncoil in some of these videos just to get a better view of it. This cochlea is where we perceive sound, and so that then is relayed to the brain through the vestibular-cochlear nerve. That's where the the cochlear part comes from, obviously, and this is then what passes through that internal auditory meatus in the temporal bone. Okay, so if we were to take the cochlea and then uncoil it, that will just make our analysis easier. So we will uncoil it. All right. And when we do, we see that there is the oval window, which will push fluid here called perilymph, and then that can then bulge outward to the round window. This portion of the space through which the fluid can pass is known as the scala vestibuli, and then when it returns towards the round window, it's passing through the scala tympani there. All right, and so the vibrations in air molecules are amplified by the auditory ossicles that push here and then push fluid, that'll bulge out there. Great, so we're pushing fluid. Okay, but as we push the fluid, there is another tube here in green which possesses a fluid. This green tube is known as the cochlear duct, and it possesses a fluid known as endolymph. So it's perilymph on the outside, and inside the cochlear duct, it's endolymph. And then the endolymph, as it moves, it's going to displace the hair cells, which are between 2 membranes. There's a basilar membrane at the base of the cells, but where the kinocilium and stereocilia are, there's a tectorial membrane. And so the movement of this fluid moves that fluid, which displaces these membranes. And then as the hairs are displaced, the ion channels move, and then the brain is aware that there has been movement in the hair cells, and we perceive that as, oh, I've just heard a sound. Okay, and so, and then that obviously is what gets transmitted along the vestibulo-cochlear nerve. Okay, now, a confusing thing, so I'm going to just show it, is, let's imagine we didn't uncoil the cochlea. What would it look like? Well, here is a cross section of the cochlea, and so you'll see that there is the scala vestibuli, where the perilymph passes before going into the scala tympani. So there and there are those 2, and in between the 2 is that cochlear duct in green, where there is endolymph. So perilymph moves here, and that can go as a movement of endolymph. And then here are the hair cells between 2 membranes. So let's advance. Attached to the basal part of these epithelial cells is the basilar. There we go. The basilar membrane. And then here you see the kinocilium and the stereocilia attached to the tectorial membrane. And so when the fluid, the endolymph, and the cochlear duct moves that will displace this, which can cause these to bend. That then changes, the electric potential, which causes neurotransmitters to be released onto these neurons of the vestibular cochlear nerve, which then transmit the message towards the cerebrum. Now, when we hear sound, two things have to be identified: volume and pitch, okay? And so volume, and so here once again, we're amplifying the sound through the malleus, the incus, and the stapes. Volume is determined by the rows of hair cells. So there are multiple rows of hair cells here, and a soft sound will displace one row. A loud sound would displace multiple rows. And so let's say I'm hearing a song or a sound of a specific pitch. It'll displace this area, but how much displacement, how many rows of hair cells will vary on the volume. And so a loud sound displaces more hair cells than a soft sound. Okay. And so then the second thing we need to identify is pitch, low sounds versus high sounds. And so what is the pitch? Well, okay, so forgive me, but I'm old, and I remember that when I was a kid, one of the commercials that you could see on television was for a cassette recorder. So, once again, before there were, CDs, there were, the cassette players. Well, there would be this woman singer, maybe an opera singer, and she would hit a high note, and then this wine glass would rupture, all right, because such was the power of, her voice. So they would tape it, and then they would, play it back and see if the tape recording could, burst the wine glass. But the point I'd like to make is that to burst that wine glass, she hit a high note. She did not hit a low note, okay? So high notes are more intense than the low notes. So when I hear a sound, okay, and it's now, causing vibrations which displace here, low pitch sounds, they just don't have as much energy to them, okay? And so therefore, they do not have the energy to displace this area because it's thicker. They can only displace this area where it's thinner, all right? And so if high pitch sounds have more energy than low pitch sounds, they then can displace this membrane, all right? But the low pitch sounds can only displace this region, whereas the high pitch sounds with more energy, they then have the strength to displace this area where it is thicker, all right? So if my brain is perceiving that hair cells are being displaced here, my brain knows I must have just heard a high-pitched sound, because only high-pitched sounds have enough energy to displace the hair cells here. If the only place where hair cells are being displaced, not at the base, but rather at the apex of the cochlea, that my brain would then realize I must have just heard a low pitch sound. And so our brain can then distinguish between different volumes based on the number of rows of hair cells, and pitches, high pitch versus low pitch, based on whether the displacement occurs here at the base for high pitch sounds or the apex for low pitch sounds. So it is the cochlea which perceives sound. In a neighboring region, in what's known as the Bony Labyrinth, so obviously this is encased in the temporal bones, there are spaces for these then loops in this bony labyrinth, and the bony labyrinth is filled with a fluid, perilymph. We have these three semicircular canals, an anterior one, a posterior one, and a lateral one in three different planes. And inside the semicircular canals, we then have a fluid endolymph, okay? And so there is fluid inside the semicircular ducts of the semicircular canals. And there are thickened regions here where in the ampulla, where we have the hair cells in a gelatinous substance, which known as the cupula. Okay, and so there's endolymph all around, but there's more of a jelly-like substance in the area where the hair cells are here in green. And when the endolymph moves, that causes this gelatinous material to move, which then once again displaces those stereocilia and kinocilia. And so then this can then tell the brain that things have moved. Once again, so if you haven't figured this out, this is coronavirus season, and I am obviously not teaching this in a regular class. The one thing I do for my class, oh, they love this, is at this point, I'll like pretend I'm put off by something, and I'll look at the clock and I'll say like, ooh, like I'm not gonna have enough time to, get to where I went to in this lecture. Would anyone mind if we stayed 20 minutes late just so that I could finish this? Is that okay? Do you have anywhere else to go? Everyone's uneasy. So you have a few students who are afraid to make their instructor, angry with them. So they're like, oh, okay. And then some are like, no, I have another class to go to. But then what I do is I'm saying, all right, so for those of you who are saying, yes, this is what was happening. You have this anterior semicircular canal. And when you move your head this way, it's causing that endolymph to move. And then it displaces, this gelatinous material, which displaces, the hairs. And now your brain knows that there is movement in this plane. For those of you who were saying, no, I can't stay, late, then there is movement in this plane, in the lateral semicircular canal. And your brain now knows there's been movement here. Whereas if you were to tilt your head this way, then you would get a displacement in the posterior semicircular canal. So your brain now knows that your head is moving because each of these semicircular canals has hair cells here in this ampulla region. Now, wouldn't the brain already know that your head is moving? After all, your brain might have given the command for your head to move. Yes, but your body is connected to your head, obviously. And that then tells not only where your head is, but where your body is. Now, I apologize. I'm not going to be able to demonstrate, this. I'll just be stupid if I try. But what I would do is I would ask my class, imagine I want to take another step. Okay, so here I am, and I want to take another step. What muscles would I use? All right, and then I go off balance like this. Obviously, you're not getting the full effect. And then I say, all right, now if I want to take another step, what muscles would I use? Different muscles. All right, so if you're going to take a next step and your body is like this, the muscles that you're going to use are different. Your brain wants to know. So your brain is deciding to take the next step. Your brain wants to know, am I here or am I here? Because that then affects the muscles which I want to use next. So our vestibular cochlear nerve and thus our inner ear help us with balance. And so the semicircular canals are detecting movement in 3 planes: the anterior semicircular canal, the lateral semicircular canal, the posterior semicircular canal. And then this information can then be sent through the vestibulocochlear nerve. So the vestibule is this area in yellow, which connects the semicircular canals to the cochlea. And here there is an additional sense. I'm going to make 2 semicircular canals go away just to get a better view. In the vestibule, there are 2 regions of hair cells. One is known as the utricle, where the hair cells are going to be oriented more horizontally. And then another one called the saccule, where the hair cells are migrated or oriented vertically, and this thickened region with the hair cells we call the macula in each case. So there's a macula of the utricle, a macula of the saccule, if you care. Okay, so the hair cells are here, and they're kind of in a gelatinous, membrane here, known as the otolithic membrane. Think of it as being, say, kind of like a jello. And then there are little pieces of calcium carbonate. Calcium carbonate are what makes up seashells. Little pieces of calcium carbonate called otoliths, which sit on the otolithic membrane in which the hair cells are embedded. Why? Well, let me just take a second and talk about this woman in this car. If the car were to accelerate, right, go from 0 to a certain speed rather quickly, the car will move first. Okay. And now notice that her body lags behind. So when the car accelerates, your body does this. Why? Because there's something called inertia. You have a resistance to movement. So just because the car moves doesn't mean that you automatically just go with it. You will resist that motion and bend backwards because of this inertia. Okay. Well, when that woman's body then gets pulled forward, there is inertia then in these otoliths. So just like the body is going to lag behind, once the body goes forward, these otoliths will lag behind because they have inertia. And as they then lag behind the movement of the body, they will then bend and distort this gelatinous otolithic membrane, and that then bends those hair cells. So your body can tell when your eyes are closed when the car is accelerating or decelerating, all right, because the hair cells are bending because the otolithic membrane was bending because of the inertia in those otoliths, which resisted the movement of the car. So this utricle has the otolithic membrane oriented in the plane that you see here, and thus can sense linear acceleration like that of a car. But in the saccule, the same setup occurs more vertically. And if you're in an elevator, you get a sense of when the elevator starts to go up and then decelerates, etc. If you were falling, you would have a sense of that. And so not only can we sense acceleration in the linear plane, horizontal plane at the utricle, but also in the vertical plane at the saccule. Okay, so these then are the senses of the ear. We sense sound at the cochlea, balance at the semicircular canals, and we sense acceleration, both linear and vertical acceleration in the vestibule. These then communicate with the vestibulocochlear nerve, so thus you see the name of the nerve. It used to be called the auditory nerve because that's what we hear with. But then it was really, wait, there's more senses to the ear. Some are coming from the vestibule. That would be the balance from the semicircular canals and acceleration. Some are coming from the cochlea for sound, so it's the vestibulocochlear nerve, the 8th cranial nerve. And that will, sorry, I skipped one. And so then the 8th cranial nerve, the vestibular cochlear nerve, formerly called the auditory nerve, then will come through that internal auditory meatus. So remember that the opening here for the auditory canal, that's the external auditory meatus on that part of the temporal bone. The internal auditory meatus, which you would see here in the petrosal part of the temporal bone. The internal auditory meatus is where the vestibular cochlear nerve, which arises here in this space. Remember that inside this part of the temporal bone, that's where the middle and inner ears are. So the nerve then comes out that opening and then reaches the brain, and damage here can cause deafness, a ringing in the ears, tinnitus, vertigo, problem with balance, and other problems. In the brain, this information will then go multiple places, one being the inferior colliculus of the midbrain. So the midbrain, once again, it develops from the embryonic mesencephalon, all right? And the area of the midbrain called the tectum is what is above or dorsal to the cerebral aqueduct. So there's going to be two bumps here. The inferior colliculus is where sound goes. The superior colliculus is where vision goes. So when you section the midbrain, depending on how you section it, you're going to get different views. And so you'll see these bumps. At one level, the bumps are the superior colliculi, which are processing vision. And then at another level, it is the inferior colliculi. And I have that somewhere, right? So it's in there somewhere. But here, for example, you see a pair of bumps on the sheep's brain. This is the superior colliculi processing vision. Here, the vestibular cochlear nerve would go into the inferior colliculi. The inferior pair of bumps where hearing is processed. So note here, there are superior colliculi, a pair of bumps, and then underneath that would be the inferior colliculi, and they're here somewhere. All right. From the inferior colliculus, the midbrain will then project to the thalamus, and there is a region of the thalamus known as the medial geniculate nucleus. And I just want to point out that, even though, we would get a, here we have the medial geniculate nucleus of the thalamus. It would be this one. It's getting its input from the inferior colliculus, and then it's going to talk to the cerebrum. So the vestibular cochlear nerve goes to the midbrain, the inferior colliculus. From there, we go to the medial geniculate nucleus of the thalamus, which then projects to the cerebrum, and a specific region of the cerebrum known as the auditory cortex, which is in the temporal lobe. All right, so here's the temporal lobe of the brain, behind the temporal bone. And here there is an auditory cortex. This is where we identify sound. Oh, I've just heard something. And then around that, in this lighter pink, that's the auditory association area where I identify the sound. So if I have a stroke that affects this area, I can't hear. If I have a stroke that affects this area, I might not be able to identify what I hear. So for example, I might not be able to identify a friend of mine's, their voice, etc. Just obviously then hearing and the other sense of the ear are therefore a special sense, because unlike say touch or pain or temperature, which can be detected here, like all over the place, these senses are only detected one place here. And instead of going to the somatosensory cortex here in red, they are going to their own special region. So the general senses, touch, pain, temperature, itch, tickle, they're all going to here, whereas hearing, balance, and acceleration are only being processed here. Okay, and so those are the senses of the ear.